Hello everyone. in the in the previous lecture, we have been discussing this notion of quotient groups. Okay, so let's recall that for two subsets A and B of a group G, we define their product A times B as the subset of G consisting of those elements of G which can be expressed as a product of an element of A and an element of B. Okay, and then we showed that if you start with the normal subgroup of a group G, then Gn is Ng for any G. Okay, and an important remark in this context is that while dealing with normal subgroups, we can safely avoid to mention whether we are dealing with left cosets or right cosets. Okay, because there is no room for confusion while dealing with normal subgroups only. Okay, and an important proposition is that if you start with a normal subgroup n of a group G and then we take two cosets G1n and G2n, then their product, by product I mean the product of these two subsets G1n and G2n as we define here. Okay, this product, and the product of these two cosets turns out to be equal to G1 G2n. Okay, and this was an important step to establish the following theorem, which states that the set of cosets of n forms a group with respect to the product of subsets. Okay, and this is what the set of cosets of n is denoted by the symbol G slash n. This is read as G mod n. Okay, this is customary to call it G mod n. This is a standard thing. So yeah, so this G mod n, that is the set of cosets of n that forms a group with respect to the product of subsets that we have defined. Okay, uh, yeah, and we are going to spend some time on this notion of quotient groups. Okay, so let's try to still continue our discussion with normal subgroups. uh, yeah uh, so for instance, when you first learn this notion of groups or subgroups, or for instance normal subgroups, then probably you have been wondering that why do we care so much for these normal subgroups. One of the reasons uh, one of the reasons is that you have already seen, uh, is that kernel of a group homomorphism is a normal subgroup. Okay, and yeah, so this is something that we have seen while discussing this notion of group homomorphisms and kernels of group homomorphisms. We learned that the kernel of a group homomorphism, or maybe I should write the kernel of a group homomorphism is a normal subgroup. Okay, and now this theorem, in this theorem we will show that if you start with a normal subgroup n of a group G, then this n is equal to the kernel of a group homomorphism. Okay, yeah, so the normal subgroups are precisely the kernels of the, or those subgroups of G that can arise as kernels of certain as a kernel of certain group homomorphism. Okay, so let's try to get into this theorem and its proof. So you start with a normal subgroup n of a group G, and then from G to G mod n you define a group homomorphism. Okay, we have to first define a map. Okay, and then the next task would be to show that this is the group homomorphism. Okay, and then the theorem states that the kernel of this group homomorphism is equal to the normal subgroup of G that you have started with. Okay, so now let's focus on the definition of this map pi. Okay, so if you take an element little g from this group G, then you send this element little g to the coset of this normal subgroup n corresponding to the element G. Okay, so we send G to Gn or Ng if you want. Okay, this is a group homomorphism. That is what we need to show, and we need to show that the kernel of this group homomorphism is exactly equal to n. Okay, to show that this is a group homomorphism, we need to show that this this pi of G1 G2 is pi G1 times pi G2, right, for all G1 G2. Okay, so for all G1 G2 in G. So this is something that you have already done. Let's see. If you look at pi of G1 G2, that is G1 G2n, that is the coset of n corresponding to the elements g1 g2, and that is equal to g1n times g2n. Okay, and by definition of pi, this g1n and g2n is equal, g1n is equal to pi g1 and g2n is equal to pi g2. Okay, and this equality is something that you have established in the previous lecture, right? So in proposition 190. Just give me a moment. Yeah, so this proves that this map pi as we have defined it, that is a group homomorphism. Okay, and now we're going to show that its kernel is equal to n. So let's take an element g from the kernel, then so then we know that so then we know that pi of g is the okay, so if we take g from the kernel, then we know that pi of g is the identity element, right? But this is the identity element of the group g mod n. What is the identity element of this group g mod n? We have already discussed here. So we know that e times n, or which is equal to n. So n is the identity element of the group g mod n, of this group g mod n. Okay, yeah, so pi of g, which is gn, so pi of g has to be the identity element, which is n, right? Okay, great. And from this equality we see that g has to lie in n, because this is, g times identity is an element of n, so g times e, which is equal to g, it lies inside gn, and gn is equal to n, so the element g lies inside the subgroup n. Okay, so g lies in n, and thus we have shown that whatever element g that we pick from the kernel of this group homomorphism pi, it has to lie in n. In other words, we have shown that kernel of pi is contained inside n. Okay, and now for any element a inside n, you see that pi of a, which is an by definition, and since we have started with an element a from n, an has to be equal to n. Okay, and this shows that n is contained inside kernel of pi. So you have proved that kernel of pi is equal to n. And as I was explaining at the very beginning, that we already know that kernel of a group homomorphism is a normal subgroup, and now this theorem shows that if you start with a normal subgroup n, then this n is equal to the kernel of some group homomorphism pi. Okay, and this is what this is what we have summarized in this corollary, that any normal subgroup of a group G is a kernel of a group homomorphism. More specifically, any normal subgroup of a group G is a kernel of a group homomorphism defined on G. Okay, by defined on G, I mean that this group homomorphism has G as its domain. Okay, this group homomorphism has G as its domain. Okay, so here is an exercise. So it is good to compare this corollary with this exercise. This exercise states that any subgroup H of a group G is a kernel of a group homomorphism defined on H. Okay, so please note the difference between this corollary and this exercise. This corollary is about normal subgroups, whereas this exercise is about any subgroup of a group G. Okay, and this corollary says that any normal subgroup arises as the kernel of a group homomorphism which is defined on G. Okay, whereas this exercise says that any subgroup arises as the kernel. Okay, any subgroup is equal to the kernel of a group homomorphism, but it has to be defined on H. Okay, it's defined on H. Okay, yeah. And of course, any subgroup cannot arise as a kernel of a group homomorphism defined on G for any group G and for any subgroup H. Otherwise, any subgroup has to be normal, and we know that there are groups which contain subgroups which are not normal. Okay, yeah. So it's straightforward to see. If you just think for a while, you'll see that you already know the solution to this exercise. Okay, so think for a while. Okay, yeah. So next we are going to learn a very important theorem related to which one learns in the context of groups. This is one of the first important theorems in the study of the theory of groups, and this is known as the first isomorphism theorem. This is a result which we have seen implicitly in some form, but now let me state it precisely. Okay, so let's start with a group homomorphism phi from G to G prime, and where G and G prime are groups. So then if we define this map from G modulo kernel of phi to image of phi, okay, this is defined as follows. Let's recall that, so first focus on this symbol. Okay, so we have written G modulo kernel of phi. So let's recall that we have seen G mod, the symbol G mod n, when n is a normal subgroup of G. Okay, so this makes perfect sense. Okay, by that I mean that kernel of phi is a normal subgroup of G. Okay, so it's perfectly fine to look at G modulo kernel of phi. Okay, that's the first thing to note. And now we are going to define a map from G modulo kernel of phi to image of phi. So let's recall what is G modulo kernel of phi. Okay, but before that, let's recall what is G mod n. So this consists of the cosets of, oops, I wrote off for two times. Okay, maybe let me write it in some color. So G mod n is the, okay, is a set of the cosets of n in G. Okay, and now you may say that I have been saying G mod n is a group, and now I'm saying that this is the set. Well, I mean, okay, so indeed there is a discrepancy. Maybe I should write that this is the set of the cosets of n in G. Okay, you write it in another color, equipped with the group law given by product of subsets of G as we have defined. Okay, so this is G mod n. Okay, then what is G mod kernel of phi? So it consists of the cosets of n, which is kernel of phi here. So it consists of the cosets of kernel of phi, and now we are going to define a map on this set of cosets. So let's pick a coset A kernel of phi. By A kernel of phi I mean A times, I mean the coset of the left coset of kernel of phi corresponding to the element A. So now if we apply this map to A kernel of phi, okay, we define the image of this coset under this map phi bar to be phi of A. Okay, this theorem says that this is an isomorphism of groups. Okay, and this is a theorem that we are not going to establish. Okay, but it would be a good idea to see that this is a well defined map. Okay, so by that I mean that that A kernel of phi could be A prime kernel of phi, and then the question is whether phi bar of A kernel phi is equal to phi bar of yeah, so A kernel phi could be equal to A prime kernel of phi, and the question is whether phi bar at A kernel phi and A prime kernel phi, whether they are same or not. Okay, so I mean, if they are not the same, then of course this map is not well defined. But anyway, so let's not get into it. So let's accept this theorem, or at least the statement of this theorem for this moment, and now let's try to see what can we deduce from this theorem. Okay, the first exercise asks to deduce the counting formula from proposition 142. Okay, so this proposition 142 states that if we have a group homomorphism phi from G to G prime and the domain is a finite group, then the order of G is equal to the order of the kernel of phi, is equal to the product of the orders of kernel of phi and image of phi. Okay, so now this exercise says that we need to establish this. Okay, of course using this theorem. We have already established this. So let's apply the first isomorphism theorem. The first isomorphism says that these two groups, they're isomorphic. Okay, we do know that G mod kernel of phi is a group because we know that G mod n is a group. Okay, and image of a group homomorphism is also a group or a subgroup of G prime. Okay, so these two are groups. Okay, and the first isomorphism theorem, which is this theorem here, it says that this map that have been defined is an isomorphism of groups. So these two groups has to have the same order or the same cardinality. Okay, so these two groups have the same cardinality. So yeah, and on the other hand, if you go back to the proof of Lagrange's theorem that I think I stated somewhere, but yeah, while defining this notion of index. Okay, so G modulo kernel of phi is equal to order of G divided by order of kernel of phi. Okay, so by this first isomorphism theorem, we know that the order of image of phi, okay, so the order of image of phi is equal to the order of this quotient, order of G modulo kernel of phi, and the order of G modulo kernel of phi is the ratio of the order of G to the order of kernel of phi. So you have obtained this equality, and that is same as having this. Okay, so thus in the context of finite groups, this counting formula was a can be thought of as a reflection or a shadow of this result of this first isomorphism theorem. Okay, great. So now let's deal with certain specific homomorphisms, and let's try to apply the first isomorphism theorem in those contexts, okay, in order to have a better understanding of this theorem. Yeah, so this is one of the fundamental maps that one studies in the studies across several disciplines in mathematics. So this is the exponential map. So this is a map from R to S1. So where S1 consists of those complex numbers Z inside C with absolute value equal to 1, and this is a group under multiplication, right? Okay. Okay, great. So this phi of x is e raised to 2 pi I x, and this map is of course well defined. Okay, and now straightforward to see that this is a group homomorphism. This follows from the property that e raised to a plus b is e raised to a times e raised to b. Okay, so this is something that we knew, and what I mean, the statement that e raised to a plus b is same as e raised to a times e raised to b for any two complex numbers a and b. Okay, so here specifically do not have any complex number. We have complex numbers of the form 2 pi I x and 2 pi I y. Okay, so what you already knew, that says, that guarantees that this map phi is a group homomorphism. Okay. And now elements of S1 can be expressed as, and in this form, cos 2 pi x plus I sin 2 pi x for some real x. So the map or the group homomorphism that we have been discussing, or that is surjective. Okay, in other words, image of phi has to be equal to S1. And now it is easy to see that, phi is trivial on Z. It's really easy to see. Okay, so if you take Z to be an integer, then this turns out to be 1. So it follows that Z is contained inside this kernel. The subgroup Z of R is contained in this kernel. And now if you take an element x in R lying inside the kernel of phi, then you know that e raised to 2 pi I x has to be 1. That is same as saying S has to be, the real number x has to be an integer. So kernel phi is contained inside Z. Okay, so this shows that kernel of phi is contained inside Z, and on the other hand Z is contained inside kernel of phi. So you obtain this equality. Okay, and by this first isomorphism theorem, we know that what do you know? We know that G modulo kernel of phi is isomorphic to image of phi, right? So what was G in this case? It was R, and the kernel is Z. So we know that the group G, which is R, modulo the kernel, which is Z. So G modulo the kernel, that is R mod Z, is isomorphic to the image, which is equal to S1. Okay, so applying the first isomorphism theorem, we establish that R mod Z is isomorphic to S1 as groups. Okay, great. And R mod Z, it's a group. Okay, so this is a normal subgroup of R. Okay, and now here is an interesting and important exercise that I think we have seen in probably in the last problem set. Yeah, at least in some form we have seen this. So let's look at this. Let's look at the statement. So to show that GLNR modulo SLNR is isomorphic to R cross. Okay. So whenever you see such notions, or such notions that a group quotiented by some subgroup, we need to just make sure. Okay. It's good to kind of it's good to make sure, or to convince ourselves, or to recall, or to see whether this is a normal subgroup of GLNR or not. Okay, whether this is a normal subgroup of GLNR or not. This is a normal subgroup of GLNR that you know, okay, or you have seen. If not, then try to do it right now. Okay, before getting into what I am going to describe. Okay, just give a pause to this video or to this recorded lecture and try to show that GLNR is a normal subgroup of GLNR. Sorry, SLNR is a normal subgroup of GLNR. Okay. Anyway, so let's look at the determinant map from GLNR to R cross, okay, which sends any matrix of GLNR to its determinant. Okay, this map is of course certainly well defined. Okay, and determinant map has a nice property. It has the following nice property, that determinant of AB is determinant of A times determinant of B for any two matrices AB inside GLNR. Okay, and this map is surjective. Okay, because if you take any element x from R cross, then look at the then you look at the diagonal matrix having x and x and a series of, or a sequence of n minus 1 ones along the diagonal. Okay, so this looks like x and then 1 and then 1. So here there are n minus 1 ones. Okay, and it starts with x. So this I mean, if you look at this diagonal matrix, then its determinant is equal to x, right? Okay, so the matrix having this entries along the diagonal goes to x under the determinant map. Okay, and yeah, so this shows that this map is surjective, this determinant map. Okay, and what is the kernel of this determinant? So kernel of this, I mean, we have already shown that this is a group homomorphism. So its kernel consists of those elements of GL and R which goes to the identity element of this group. What is the identity element of this group R cross? It is equal to 1, right? So you have to look at, so the kernel of this group homomorphism consists of those elements of GL and R which has got determinant equal to 1. Okay, the same as saying we are looking at SL and R. Okay, so the kernel of the determinant homomorphism is equal to SL and R, and by the first isomorphism theorem that we have just studied, from that it follows that the group G modulo its kernel, okay, the group G modulo the kernel of the homomorphism that we are considering, G modulo the kernel of the homomorphism that we are considering is isomorphic to the image of this group homomorphism. Okay, and this determinant map is surjective, so its image is equal to R cross. So this quotient is isomorphic to R cross. Okay, once again we see something that we already knew, right? We already knew this group Z mod nz and mu n. Okay, here are just two remarks. So as I stated in the previous lecture, that Z mod nz can be thought of in one can think of this notation in two ways. So first, the obvious thing, the way we have defined Z mod nz couple of lectures back, maybe 5 or 6, or I don't remember. Okay, so the way we have defined Z mod nz couple of lectures back, and the way Z mod nz should be as per the, what are the notations? Yeah, as per this notation that we have introduced in the very previous lecture. Okay, and this remark says that there is no confusion. Okay, because the group Z mod nz that we have defined earlier is same as, okay, this is not only isomorphic, this is equal to, okay, this is equal to the quotient group Z mod nz. Okay, and from now on we will actually think of Z mod nz as this quotient group. Okay, so why I have been mentioning all that? The reason is that we are dealing with this, we are about to deal with this, so it's good to clarify. Okay, yeah, so Z mod nz is G mod n. Okay, you'll think of it in this form, where where of course the group G is equal to Z and n is the normal subgroup nz of Z. Okay, yeah, so we already know that these two groups are isomorphic, but we are going to use the first isomorphism theorem to show that these two groups are isomorphic. Okay, so let's define this map from Z to mu n, which sends an integer k to e raised to 2 pi I k over n. Okay, and okay, whether this is well defined or not, that's the first question. E raised to 2 pi I k over n is an nth root of unity, that is this raised to n is equal to 1. So this is an element, sorry, so this is an element of mu n. So this map phi is well defined. Okay, did I, yeah, I think I already mentioned that the determinant map is well defined, because if you take an element from GL and R, its determinant is non-zero, so it's an element of R cross. So it was on the map that we have been considering earlier, it's well defined. Okay, now so now if you look at this map, then you see that this is also well defined. Okay, and now to see that whether this is a homomorphism or not, you apply this property of exponentials, and that tells us that this is indeed a group homomorphism. Okay, and now to look at its surjectivity, this is going to be surjective, we know, but we need to prove it. So if we pick an nth root of unity, that is if we pick an element from mu n, we know that it is equal to e raised to 2 pi I k over n for some k. Okay, so of course it follows that this map is surjective. Okay, by the very definition of this map. Okay, so we see that image of this group homomorphism phi is equal to mu n. Okay, now one can see that this map phi is trivial on the subgroup nz, and is also, one can also see that if you take an element from the kernel of phi, it has to lie within nz. Okay, so it follows that kernel of phi is equal to nz, and by the first isomorphism theorem we know that this group G modulo the kernel of this phi, which is nz, so the group G modulo the kernel, which is nz, that is isomorphic to its image, which is equal to mu n. Okay, so you have established this isomorphism as an application of the first isomorphism theorem. As you see, we have been using first isomorphism theorem to establish something, or at least some statements that you already knew. So I'm not so sure whether I mean, I don't remember whether you knew this or not. Okay, I mean, at least in this specific form, but you of course knew this isomorphism, that these two groups are isomorphic. So I mean, so what I'm trying to point out is that the first isomorphism theorem can really be thought as a more general result, as a can be thought as a result more general than some of the statements that we have seen so far. Okay, and it has got wide ranging how to say applications, or this gets frequently used in the study of groups. This gets really frequently used, and for that reason this is called the first isomorphism theorem. And now you may wonder whether, I mean, if this is called the first isomorphism theorem, whether there are second or third or fourth isomorphism theorems or not. Yeah, so there are second and third isomorphism theorems, and okay, I do not know if there is any fourth isomorphism theorem. Okay, great. So let's conclude this lecture here.